but spirits are high. Let's do this thing. Let's do a little bit of review because regression is the thing that we haven't seen on a test before, and so I want it to be really ingrained. And at first I had these kind of lofty goals of, oh, and then I'm going to do this, and I'm going to do this, and I'm going to do this. But then we do a common final exam, so there's really no point. And so I've decided to scale it back and just do review, so final exam review next week, okay? And so we'll finish what's left of the slides, just a little itty bitty bit of the slides today, and then I'll open it to the floor and we can go through test 2 questions, because I know there were some that weren't that good or could do better. And so, and we'll go through those together, and then we'll do more review, final exam review next week. So regression. Should remind me, okay, it's got that clean screen. Do you guys like it when you can see my pens or no? Looks better, but it might be out of nowhere. Confusing. Now that I know how to change it. Do you like it when it's like this? That's what I see. I'm hearing no preferences. I don't know, just do your thing. All right. So regression, our main goal is to build a regression line. Y hat is B naught plus B1 times X. Now that's on your formula sheet, of course. And so what else is on your formula sheet? Where B1, oops, B1 is the slope. Or I guess it probably says something like, oh, sorry, by the time I get to this class, I've already been writing for 2 hours, and it shows. I think it says something where the slope is B1 or something like that, but B1 is R times SY over SX, I want to say, but let's confirm. Yeah. Times SY over SX. And where B naught or B0 is the intercept. Oh, I'm fancy. Auto deselect. Okay, got it. I don't know why it decided to tell me about my settings now, but whatever. Is the Y intercept words. So B0 is Y bar minus B1 times X bar. It's important that you find B1 first because, and that's why they're in that order. Otherwise, you would probably put them in B0, B1 order, but to kind of, oh, hello. Hello? Anybody home? It's from the calls coming from inside the house. There you go. All right. We have to find B1 first. So we have to find the slope first, because then we use the slope to find the y-intercept. But once you have those things, then you can plug them in for B naught and B1, and then you have a line, right? Y equals mx plus b. And so to solve this, which I will make you do, right? Find the slope will be one of the parts. Then interpret the slope. We'll talk about that, more review. Then find the y-intercept, or I might just say intercept. All right, do that. Interpret the intercept. Is it meaningful? right? These are kind of the go-to questions that you will see on the final exam. But to solve these, we need 5 pieces of information. And they'll be given. Let's see if we can find those 5 pieces. I need the correlation, but that one's a pickle, so I'm going to parking lot it for a little bit because, as we said last day or on Tuesday, there are 3 ways that I could give you the correlation. Okay? And so we need the standard deviation of the y's, the standard deviation of the x's. I mean, I need the mean of the y's and I need the mean of the x's. And so I need to give you x bar and the standard deviation of x. And I need to give you y bar and the standard deviation of the y's. Usually in a blurb. Okay. You'll also have, I'm going to be nice and I'm going to give you the scatter plot. Okay. So it might look something like, usually I do a positive relationship, but let's spice things up. Do a negative relationship. Why not? Yeah. Then whatever's on the x-axis is your x, and whatever's on your y-axis is your response variable, so that's your y. So if I give you labels for x and y, and I also tell you that, okay, the average of whatever this guy is, right, was this, then that's your x bar. And so mapping the information to the correct variable is going to be super important, right? Because if we think about this fraction in particular, it's going to haunt us in the slope, right? So if you get that wrong, then it kind of haunts you. I make sure that you don't lose too many marks, but it is important. So you lose some marks. Think about 2 divided by 1 is 2, but 1 divided by 2 is 1/2, right? So you would get drastically different values. Okay. And so this I would give you in kind of a word format, kind of a paragraph, right? They found the mean was this and the standard deviation was this, and the mean of this was this and the standard deviation of this. And I also need to give you R. There are 3 ways I could give you R. Give you R, the correlation. 1, I could just say what it is, right? I could say the correlation between x and y is R. Wouldn't that be nice? Probably not. But if I do, then you'll say, wow, she's so nice. Don't have to worry about it. X and y would be replaced by the variable names, right? So I'm not going to say x and y. I'm going to call them, you know, whatever x is and whatever y is. What's the other way? I could give you the covariance, right? Given the covariance SXY on your formula sheet, right? R is SXY divided by SX times SY. Nice. Notice SX and SY, you would have those here, right? SX and SY. So it's really just one more component that you would need to kind of put together to find the correlation. Remember, the correlation is a measure of the strength and the direction of a linear relationship. And so it has to be linear, right? And so, but if it's negative, right, then we have this negative relationship. Whereas if you have a positive relationship, it should be positive. And then the closer to 1 it is, the stronger the relationship is. So then if I give you the pointer, the covariance, right, then you can solve for the correlation that way. What's the last way, the new way that we introduced just on Tuesday? I could give you the R squared, right? The R squared. Maybe we'll say, given R squared, find the correlation. It would say something like, I don't know, 72% of the variability in Y is explained by the least squares regression line on X. What would you do here? So last day we talked a lot about, okay, having that kind of mental trigger. If you see some percentage or proportion of variability in a sentence, kind of, then you need to think R squared. Okay, it's either asking you to find R squared or it's giving you R squared. Okay, and so what you would do is you would say R squared in this case is 0.72. And I guess somewhat confusingly, when you take the square root of capital R squared, it becomes a negative R, but the correlation squared is just your R squared and vice versa. And so then the root of 0.72. So as an example. But you have to remember that when you take the square root, you have to tack on that plus minus. So that's where you need to go back to your scatter plot. Okay. From the scatter plot, decide if R is positive or negative. And then you have the correlation that way. Right? That's probably the hardest way to find R, right? Because it involves that extra step of, if we have a scatter plot like this, right, then I would need to tack on the negative or use the negative version of the root of R squared. Always working with the decimals for our math. Okay. Okay. So those are the 3 ways that I could give you the correlation. Okay. Everything else is pretty standard. Okay. So I wasn't going to do it until after, but a regression question is going to ask these things. Okay? And so sometimes the order has to change, because if you need, right, if you need R to calculate the slope, then if I'm going to give you R in this last way, right, if I give you R squared, then that has to float to the top, right? We have to deal with that first. usually if I just ask you to find R squared, it's at the bottom. And so, or kind of towards the end of the questions, but the general layout of a regression question is going to be, I give you a scatter plot. Step 1, describe the relationship. That's where you're going to talk about the strength, the direction, and whether it's linear versus non-linear. As a hint, we only know how to fit lines, and so it better be linear, right? But you do have to say that it's linear. It's one of the conditions. And so you do have to say that, okay, I can model this with a straight line. It looks like a linear relationship. Okay. If you can see some sort of pattern, I would call it strong. You can get fancy, but I'm really only looking for kind of strong relationship or a weak relationship. But if you see any sort of pattern, I would call it strong. You can throw in modifiers like moderately strong or moderately weak if you prefer. But I'm just looking for, are you talking about the strength of this relationship? And the direction, there's only 2 options, right? It's either positive or negative. Good. So usually I put that on there hoping that it's easy marks, and then I'm so disappointed when people don't get it, but you guys are gonna get it. I know it. Next thing, depending on how you get your R, maybe I would say 72% of the variability in Y is explained by the least squares regression line on X. Find the correlation, right? That would kind of get snuck in here. But just in general, once you have all the information, those 5 pieces of information that you need, I would say find the slope. Fair enough. Okay. We just talked about how you're going to do that. That's on your formula sheet. Nothing crazy. It's just about having mapped the information to the correct variable, right? After you find the slope, I'm going to get you to interpret the slope. Interpret the slope. And we did it last week and reviewed it last day, so I'm not going to write it out. But what is interpreting the slope? The slope is for each unit increase in X, right? I expect a slope increase in the predicted value of Y. One day, hopefully in our lifetime, it would just write it out, what I said, and maybe nicer. I can just think it and it'll just do it. Not yet though, or not available to me. But you're going to interpret the slope in terms of the variables, right? Not generically, but whenever we say X and Y in the slope, you're going to replace them with the variable names, right? But nothing too bad. Then find the intercept. We just talked about that. That's on your formula sheet, right? And so, right, once you have your slope, you can use that to find your intercept. Now, this is where marking takes a long time, because if you didn't find the right slope, then I'm not going to penalize you for that all the way through. You don't get the slope marks, but as long as you follow through with that slope, then that's fine by me. Okay. And so, right, but it takes some brain power. It's always easier if you just get it right. Would you? Once you find the intercept, you have to interpret the intercept. Now, what I don't want to see is I don't want to see blanks for the interpretations, because those are just things that you can kind of make your way to using the formula, right? So what's the y-intercept or the intercept? The intercept from up here is the predicted value of y when x is 0, right? You want to talk in terms of the variables, right? But the intercept is the predicted value of y when x is 0, right? Even if you're drawing a blank and you say, okay, shoot, Emily, I cannot figure out how to find the slope. That's fine. Just look at your graph and pick a reasonable slope, right? Here, I would do something simple like it's negative. And so it has to be negative, the one that you pick, but maybe -1. Sure, why not? Right? Just say, hey, I forgot how to find the slope, but I'm going to use slope of -1 for the rest of this question. So you can still carry on, right? And that takes a little bit of knowledge, but if you're drawing a blank, it's better than nothing, right? Just tell me what you're about to use. You'll get marks for finding the slope, but you can keep as many marks as possible. Okay. Same thing for the intercept, just pick something that looks reasonable, right? You'll have the scatter plot so you can kind of figure it out. Yeah. So after you find the intercept, you're going to interpret the intercept. Usually I do a follow-up with, is it meaningful? That's not a yes or no question. You have to back it up, right? And so interpreting the intercept, it's the predicted value of y when x is 0. So really what the meaningful part is getting at is, do we care about the predicted value of y when x is 0? Does x equal to 0? Is it ever going to happen, right? If it will, then sure, it's meaningful. If x equals 0 would never happen, then it's an extrapolation, right? And so then it's not meaningful. The way lines work, lines go from -infinity to +infinity. So the y-intercept, it's going to cross the y-axis at some point. So whether it's meaningful or not is really just, okay, fine, I will add, right? Your argument has to be about x equals 0. Do you care about x being 0 or no? And we did do that thoroughly, but I think it was maybe last week and Tuesday. So interpret the intercept. Then sometimes I do freebie marks, like write the least squares regression line, or maybe I'll say construct the least squares regression line. That sounds hard, maybe, but what's that really doing? That's just this, y hat is b0 plus b1 times x with your slope and your intercept put into it, right? I do that one for a free mark. You should be able to do that. And again, as long as you follow through with whatever you told me your slope and your intercept were, then I'm happy. Then, why did we build this line? It was so that we could use it to predict values of y, right? Y hat is the predicted value of y. And so predict y when x equals something. I give you some value of x, you're going to plug it into here, right? You're going to look out for extrapolations. right? And so usually I do a follow-up, which is the same. Predict y when x is something, but this something is going to be outside the values, the range of x's. Or maybe, can I just say an extrapolation? So to nudge you in the right direction, I follow it up with, do you trust this prediction? That's where you're going to talk about no, because it's not a yes or no question. You're right. You have to back it up with no, because x equals 4, right, is not in the range of my data, or it's not from the values of x that I built my line from. Or you could just say no, because it's an extrapolation, right? So then you don't trust this prediction. Clean this up. And then the very last part would be, if I haven't given you r squared to find r, then usually I float it to the very end. And so find the percentage of variability in y explained, bless you, by the least squares regression line on x. And that's it. You can do that. I think. Feeling pretty good. I will grab a screenshot here because, well, now I'm, oh, test time. Okay, let's see here. Did I make it available? Well, I guess we'll see. Student. Oh. So at the very end of our Moodle page here, bring this in. I've got a rough final exam outline. And we'll come back to this. I also posted practice for the final with solutions. And so right at the very end here, least squares regression analysis, 10 marks approximately. And so, yeah, because I'm being all vague about it. Okay. A confidence interval. A confidence interval. A hypothesis test. A chi-square test. Got choices. Although I realize that I feel like this is pretty telling. A confidence interval, then a chi-squared, and then confidence interval, hypothesis test. Anyways, doesn't mean anything. Okay. So 10 marks. So what does that look like? Well, there's probably one kind of floating around here. Can't remember if I do easy gimme marks. No, I think 1 mark, 1 mark, 1 mark, 1 mark, 1 mark. Oh, there. Then 2 marks for the, do you trust this prediction? Because I want you to say extrapolation. Goals. And then 1 mark. Just little 1 markers. But there you have the general layout of a regression question. So here, see above. Any questions before we? So what I want to do is final exam review next week. So we'll go through this list of things, right? Talk about, kind of a refresher. But what I also want to do is if you bring your test questions that you want to go through together, then we'll do that. And so bring test questions to work through together. Right. Because those test questions are curated to guide you, right? So for example, if I made you do a 1 sample proportion, I think confidence interval, then might be nice to be able to do a 1 sample proportion hypothesis test, right? That kind of thing. And so you can always do both for all the questions. Rude. Okay. And so if there's anything that you kind of, or any practice problem really, what I will do is I'll do you the favor of telling you if you need to worry about it. So if it's a question that you don't need to worry about, I'll tell you, because I don't want to spend time doing questions that you don't really need. Pick up here on Thursday. Well, here we are on Thursday, but any questions before we? No. Uh-oh. Although having the pencil over there is really saving off Alzheimer's for me. When you have to like change your routine, can't handle it. Have to stay strong. What were we talking about? Oh, wow, I really don't know what this question is about. And I deleted the slides leading up to it. Something about percent Hispanic in LA, but what were we trying to do? This looks better. This we can handle. I don't know about this map, what we're supposed to learn from there, but now familiar territory, a scatter plot. Phew. So what can you say about the relationship about the percentage of college graduates and the percentage of Hispanic in a sample of 100 zip code areas in LA? Oh yeah, when I was reviewing this, 100 zip codes, I only know one, 90210. And when I signed up for a Hotmail account, you had to live in the States. That's how old I am. And so I bet you there's so many Hotmail accounts that were just created with 90210 as the zip code, because that's what I did. Anyways. So, funny times. All right. So, what can we say about this relationship? Describe the relationship. Okay, that's good practice. I'm going to rewrite this as describe the relationship. between the percentage of college graduates and the percentage Hispanic in LA or in these zip codes of LA. But before we do that, what's your X and what's your Y? We need to know, and we need to remember that this is your X. So then this is your X, the percentage Hispanic. This is your Y, so your response. So then your Y is the percentage of college graduates. Okay. And so here, to describe this relationship, right, we've got I see a pattern. I see kind of a strong pattern here, right? If I kind of throw some bands on there, rough approximations, as soon as you can see a pattern, we say it's a strong relationship, right? As soon as it's not a cloud anymore, then you say it's strong or moderately strong. In this case, I would say it is strong. And so this is a strong negative, right? Because I've got this downward strong negative linear. We didn't have an option there. I said linear versus nonlinear, but we don't know how to deal with a nonlinear relationship. And so even if for a moment here, let's ignore these, you were tempted to say that, oh, it looks like this. That could be a better model, yeah? A nonlinear model, but we don't know how to fit nonlinear models. And so for the question to work out, we have to say it's linear, right? Reasonable to model it with a linear relationship, right? Reasonable enough, right? And so linear relationship. So I want you to resist the urge to get all fancy and tell me it's nonlinear, because that means you can't answer the rest of the questions, right? Telling me it's nonlinear and then fitting a line to it is bad, right? Whereas you say, oh, I only know how to fit a straight line, so it better be linear. That's fine. So what we do in practice anyways, if we don't know how to fit nonlinear relationships. Okay. So that's one mark, but you have to touch on all three, right? You have to talk about the strength, the direction, and whether it's linear or nonlinear, right? Then you get full marks. Yeah. This looks weird when it's on the slant here. Let's do that. I think we're gonna get, okay, we won't, but that's okay, right? In the blurb, I would tell you in the sample of 100 zip codes, right? What's your sample size? 100, right? The mean percentage of college graduates was, I don't know, looks like about, let's say, a little bit less than 50, right? Just kind of looking at the range of my Y's is somewhere between 0 and not quite 100, right? But there's more points down here. It looks like kind of rough approximations. I would say maybe 45% or something like that. But it would be in the blurb with a standard deviation of, I don't know, 2% or something. Okay. And then the percentage of Hispanic, the mean percentage Hispanic was, let's say 50% with a standard deviation of 5, something like that. Yeah. And so when you build your line, right, if you have percentages here then you're just gonna keep those percentages. You don't have to worry about converting them to decimals, which is usually what we do when we do math on percentages. But in this case, if the units are just percentages, you can just keep them as percentages. Okay, good. So in this case, we're given the output. This is, I think this specifically is our output, but this is from, you know, software, Excel, or R, or SPSS, if you're of the social sciences, they love SPSS, but it's a lot of click, 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 click. Okay. We saw this output last day, right? This is an estimate. Hey. You want to take over? Ah. This is the estimate of the intercept. He never takes me up on that. And this is the estimate of the slope, right? It's an estimate because it's based off of our data, but what can we do? I can use this output, right, to draw or to construct my least squares regression line, right? So here, this means that my B naught is 0.7290 and my B1 is 0.7527. So then maybe I'll write it in terms of, do it in both ways. Y hat is 0.7290 minus, because it's plus B1, but it's a negative B1, so minus 0.7527 times X. If we want to talk about these variables in terms of college graduates and Hispanics, then Y, and this is where you would refer to your scatter plot, is the percentage of college graduates, right? So maybe we'll shorthand it to percentage grads. If you're proper, I'm lazy, so I didn't write percentage of college graduates, but you could. The predicted percentage of college graduates is 0.7290 minus 0.7527 times the percentage Hispanic, which I guess should be capitalized. And that's why in the output, right, we have the coefficient of the percentage Hispanic, because the percentage Hispanic is the X. If we have to interpret the slope is this value here, right? That's the slope. Interpreting the slope. That's the one that is for each unit increase in X. So for each unit increase in percentage Hispanic, we expect a slope increase in the predicted value of Y, which is the predicted percentage of college graduates, right? I did was it a double negative? A negative increase is a decrease, but I don't typically bother with that. Here we have the options, and so we can say decrease, but I wouldn't worry too much about it. You can say a negative increase, and that's technically correct, right? That is a decrease, but a negative increase works. It just sounds weird. And so for each unit increase in the percentage of Hispanics, so for let's see here. I hate reading these. They're so hard to read. Does it all look the same? Let's start chipping away at these. A looks okay. A 1% increase in Hispanic residents in a zip code area in LA is associated with a 75% decrease in the percentage of college grads. I'm not going to commit quite yet, but I'm going to read the rest of them and see if I can kind of pick away at these. And so a 1% increase in Hispanic residents in a zip code area in LA is associated with a 0.75 decrease in percentage of college grads. So 75% decrease or a 0.75 decrease. Now I don't know the units. Okay. As I suspected. Kind of a curveball. I don't need you to weed through the multiple choice on the exam. I just need you to interpret the slope. So how about I just give it to you. 0.75%, because the percentage is for the Hispanic, right? Percent Hispanic, but this is just the value, right? The slope is just the 0.75. So you're not going to convert it, but that's tricky. I'm not going to do that to you. The X's and the Y's could be in percentages just because it's really common. But just stick with the units. Don't alter the units. Okay. We introduced this last day, but as you saw on the list of questions, it's not something that I'm going to ask you, and so we'll just kind of run through it for completeness, but it's not something that I'm going to expect of you. So maybe as a bonus, that might be nice. Do these data provide convincing evidence that there's a statistically significant relationship between the percentage Hispanic and percentage of college graduates in zip code areas in LA? And so the significant relationship is going to talk about the slope. In fact, it's testing what? A slope of 0. Think about a slope of 0. A slope of 0 would look like this, right? That's no relationship. Doesn't matter what value of X you plug in, you're going to get the same value of Y. And so there's no relationship here. Okay? And so what we're testing is whether beta 1 is equal to 0, meaning there's no relationship, versus the alternative hypothesis that beta 1 is not equal to 0, that there is a relationship. We don't typically do one-sided tests for the slope because we just want to know if it's significantly different from 0, right? Is there some sort of slope? Because then we can just look here and say, okay, it's negative, so then it's negative, right? Or it's positive, therefore it's positive. But just for any relationship. So then we have the estimate, we have the standard error. The estimate is how far from 0 taking into account the spread. That's what this T is doing. So here, kind of snake it through there. T is the estimate minus beta 1 divided by the standard error of the estimate. You can try it. Beta 1 is 0 because we assume the null hypothesis is true still, right? That's always going to be the case. But then it also gives you the p-value, very, very small, approximately 0. This is the p-value for this test. Right? So it kind of bypasses step one. Usually I make you calculate the test statistic and find the p-value. But when we use Excel or any sort of software, it usually does those steps, right? So the critical steps for us to be able to do are really just stating the null and alternative hypotheses and then using the p-value to draw your conclusion. And that's why in my marking scheme, right, calculating the test statistic and finding the p-value, that's only 2 marks out of 7, right? Because the meat and potatoes of what you need to do are stating your hypotheses and doing your conclusion, right? So with a p-value of approximately 0, right? Not 0, because that would mean that t is at infinity, or in this case, negative infinity, and that's not the case. And so it's approximately 0. So yes, the p-value for the percentage Hispanic is low, so it's very, very small. Low meaning less than our alpha level, let's say 0.05. Less than alpha equal to 0.05, which means we have enough evidence to reject H naught. H naught was that the slope is 0. Right. And conclude that the slope is significantly different from 0, meaning there is some sort of slope. Yeah. Nice. This is all assuming that our sample is representative of the population, right? And so all our results rely on that our sample represents the population. So that's why we spent so much time in the beginning kind of talking about how do you sample randomly, right, for it to be representative. And so here, how reliable is this p-value if these zip code areas are not randomly selected? Well, not very, right? Because then, right, if they're not randomly selected, then they're not necessarily representative of the population. We didn't talk about the degrees of freedom for the t, right? And so here, t, in this case, t always needs degrees of freedom. The degrees of freedom for the slope in a simple linear regression. And I don't want to highlight it because we don't need to know it. But it is n-2. Right? The reason for the n-2, just for a little deep dive, is because we're estimating 2 things, right? We're estimating the intercept and we're estimating the slope. And so then we've used up 2 degrees of freedom. And so that's where the n-2 came from. That doesn't matter. But usually people are like, where did the degrees of freedom come from? Maybe not. What does a confidence interval look like? Any confidence interval looks like this. The estimate plus minus some critical value. In this case, it's a T star, but it could be a Z star. So a critical value, and I'll toss on a T star in this case, times the standard error of the estimate. This is back to the twins, the biological IQ and the foster IQ of the twins. I don't think we can do those studies anymore. Separate 27 twins at birth, identical twins even. But it was done, you know, relatively recently in 1966, so relatively. So then our estimate, if we want to make a confidence interval for the slope, right, because our estimate is just based off of our data, right? And so we understand if we took another random sample of 100 zip codes, we would get a slightly different estimate of the slope and the intercept, but that's how we're going to build a confidence interval. And so in this case, we would get 0.9014. That's the estimate for the slope. Plus minus some, and I'm going to say T star here at n minus 2 degrees of freedom. I guess we could find it. N was 27. So the degrees of freedom is 27 minus 2, 25. All right, we've got the skills. Let's do it. 25 is even on the line. And I wanted to make a 95%, 95% confidence interval. So I get a T of 2.060. See if I can remember that. T star equals at 25 degrees of freedom. So when we shorthand, when we kind of grow up a little bit, the degrees of freedom, you just put them as a little subscript on the T. Okay, so that's why I wrote T star 25 is 2.060. So maybe let's replace that there. Times the standard error of the estimate, which is 0.0963. I see it. Right next to it, actually. Hope it's right. Looks good. Can calculate the interval, right? But it's not something I'm going to get you to do, but maybe for a bonus, right? Be prepared to read some sort of output like this, right? Maybe a hypothesis test for the slope, right? Is there a relationship, or maybe a confidence interval? How do you interpret this interval? We always have to interpret the interval. Let's assume it's these numbers, 0.7 and 1.1. Remembering that we're talking about the slope. So we are 95% confident the interval from 0.7 to 1.1 captures the true slope of the relationship between Foster IQ and bio IQ. But that last little bit, the true slope of the relationship between the Foster IQ and the bio IQ, you would just steal that from the question, right? Oh, I guess it just says slope parameter, but I would just say I would have it so that it says the slope of the relationship between the Foster IQ and the bio IQ, so you can just steal it. Little recap, but nothing crazy. In fact, you're not going to have to do these calculations, right? And they're not on your formula sheet, so I can't even really expect you to beyond a bonus question type of scenario. So if you have a sample, so the most important part here is that kind of tying it all together. If you have a sample that's not randomly selected, so it could be biased, not necessarily, but it could be, and you don't know, then the results will be unreliable, and that's really bad. But with that, how can I do a fancy The end. And I know you're so sad about it. You did it. I think. Yeah. Like I said, I had grand ideas. I'm gonna show them this, I'm gonna show them this. And then I thought, well, it's not on the final, so what's the point? Let's just practice for the final. Good job, guys. You did it. No new material, just practice now. Weird timing. Whole hour, huh? Or 50 minutes, I should say. What are we gonna do? It's up to you. We can do practice problems, can go through some test questions. Or if you've got places to be, that's fine too. I do as well. I'm getting nothing. No, just, I don't know. I don't want to say the wrong thing. Maybe we'll do this. How about I'll pause the recording and then you can flip through your tests if you have it. And here, start the recording. Okay, so we're in test 1, question 3. And I'm going to tack it on at the end here. Oh, paste. Okay. And this is version 2, I think. Okay. For completeness, how about we start with how many manatees died in the Americas between 2004 and 2008? And so that's just, it doesn't matter how they died and it doesn't matter where they died. It just is the total. And so the total, I don't think there was anyone who didn't get that one, so that feels good. Nice. What percentage of all manatees died from a boat collision in the Amazon basin? And so the all manatees is going to be your denominator. And that's the tricky part. So of all manatees, which is 349. And then what does that leave us with here? That means a boat and Amazon. Right? So it had to be a boat collision. So one of these. And the Amazon basin. Let's see here. Which I'm going to go with 55. I do struggle with these as well, but so I'm like, I hope.
There's one from the practice, and it was like 2, and I had to read it 5 times because they both sounded the exact same, but they're just like of or and.
Yeah.
Or something like that.
And I find that the key is always to figure out what it's out of, right? Kind of the denominator, and then that'll kind of set you up, because if this is the denominator, then the temptation of doing boat collision 55 over 214, for example, right? Then you can resist that temptation and say, no, it has to be over 349. So then what, right? Which I think is what was kind of the most common, right? But that's the percentage of manatees in the Amazon basin that died of a boat collision. Different. Haha, what percentage of Caribbean manatees died from other causes? So of the Caribbean manatees, now I'll erase this here. Of the Caribbean manatees, they had to die of other causes. But again, the denominator is the Caribbean, which is 128, and then 17. And you can just leave them as fractions. You don't have to convert them to, it does say percentage, but at this point, and for the final exam, I'm pretty breezy, right? There's no more lessons to learn with hard marking on the final exam. So I am just a little bit more lenient on the final exam because it's a stressful time. And also, like I said, there's no more lessons to teach you. So I'm not going to do that. So if you just, it always feels like, oh, that could be my car, I guess. I don't think so. Although I'm parked right there. What percentage of all manatees died in the Gulf of Mexico? That was kind of boring of me. Because now what's the denominator here? Is that 349? And they had to die in the Gulf of Mexico. So let's see here. Of all manatees died in the Gulf of Mexico, we don't care how, so it's the total. This one's the tricky one. There's a couple of ways that you could do it. Okay. What percentage of manatees died in the Amazon basin or by boat collision? So first things first, again, what percentage of the manatees? This would be your denominator if you chose to go that route. Okay. But here, the key is to deal with this or, right? And so the Amazon basin here, this, or boat collision. So we're talking about this total or this total, but those totals counted 55 of those twice, right? So you need to subtract the overlap. Another way that you could do it is you could say, well, that must be 86 plus 73 plus 55 plus 35 plus 15. Then you're only counting this 55 once. Doesn't matter how you get there, right? Whether you use the totals and subtract the overlap, or you ignore the totals and you just add up the ones that satisfy that criteria. I'm going to do with the subtraction of the overlap. 214 plus 105 minus 55, right? Just highlighting that minus. I guess I can do both. Or 86 plus 73 plus 55 plus 35 plus 15. Either way, you should get the same number. A logic dictates. 214 plus 105 minus 55, I get 264. And here, just to check, 86 plus 73 plus 55 plus 35 plus 15, phew, 264. So then you get 264. It's another way you could do it. You could take it way back to the theory. Or the probability of A or B is the probability of A times, or plus the probability of B minus the probability of A and B. A probability is a percentage, right? So the probability of A, the Amazon basin in this case, the first thing, the probability of A is 105 over 349. Plus the probability of B, which is dying by a boat collision. Hey, conveniently A and B kind of work out. Be weird to call this A and this B, but 214 over 349, but you could. Plus minus the overlap. There were 55 out of 349. But this all has a common denominator, 349. And so now I have 105 plus 214 minus 55 over 349, which is exactly what we did here. So you don't need to use the probability formula, but for me, I find that it's helpful, right? But like I said, you can kind of cobble it together any way you want, as long as you subtract the overlap. Now let me just see something here. Okay, not quite. Yeah. Never mind. Usually what I was checking is I would have made you find each of these components in the previous parts, and then you can just link them together. I didn't do that in this case. Rude. All right. Nice. What's an extension we could do from this question? Are these independent of each other, right? Is the cause of death independent of the location? That's a chi-squared goodness of fit test, right? And so that's why we spent time kind of working with the contingency table, is to build up to the chi-squared goodness of fit test. I don't want to do that because the expected values are really long, right? What would you have to do? The expected value for this cell would be 214 times 128 divided by 349. And do it for all of them. Or just use Excel. Not on the test though, bummer. If it's a chi-squared test of independence, I'll do this a similar thing to what I did on the test, where I don't make you calculate all the expected values. This one was nice because you were able to figure it out. If you know how the totals have to add up, you could have gotten there without the formula, and I was fine with that. But on the final, I would expect you to know how to, I'm not going to give you all those clues. And so kind of a warm up, if that's the chi-squared that I select. And I would also give you the chi-squared that you would have to calculate, right? Because that's a big, nasty calculation, right? First, you would need to find the expected count in each of these cells, then take the distance, the observed minus the expected, square it, divide it by the expected, and do that for each of the cells, and then add them all up, and that's your chi-squared. So when I said, assume the test statistic is 20 something, that saved you a lot of work, right? Then you can just go ahead and do it. But that's what software is for anyways. Okay. Nice. Cool. And thank you. You saw me floundering. Come on. Any others? Let's do it. The chi-squared test. Should we do version 1 this time? Why not? I actually think I might have kept them the same for, I got lazy. / ran out of time, more likely. I'm just going to copy these pages and delete the text. Please stay on the line.
Thank you.
See ya. Delete, delete. Can I keep this? It's so much writing. Thanks. But I do want to talk about this one. All right. So in this case, you don't even need to read the question. If you see a contingency table like this, and it's not, the one that we just did, then it is a chi-squared test of independence. And so it has to be a chi-squared test of independence. See ya. So once we know that, okay, fair enough. Now she has a problem. She runs out of certain beans faster at some locations, and so she collects a random sample of 250 transactions across the 3 locations, and then the type of coffee. And so we want to know if, well, later, if there's a relationship between the location and the type of coffee that she sells, or if they're just independent of each other, right? Knowing the location tells me nothing about the type of coffee that's going to be sold there. So 3 missing values, like I said, so here you could say, okay, I can find C because 15 plus 13 plus C has to be 50. But let's assume that you can't do that. So then A would be the row total 110 times the column total 65 divided by the total, which is 250, which is some number. $28.6. And we keep the decimal places, right? Because they're just expectations. And the expectations never happen. It's just what we would expect over an infinite number of times. For B, 110 times 110 divided by 250. Oops. and C 50 times 110 divided by 250. 22. Nice. The conditions for a chi-squared test, the list of conditions was kind of bad, so I was pretty lenient. As long as you checked off that you have to have at least 5 expected counts in each cell. And we always have to check the first one, or the randomly selected sample, or the samples in this case. No, a sample, one sample of 250 transactions. I did say that this one was okay. Technically, it's not okay, because if we assume that the samples are independent of each other, the reason I was okay with it is because we have to start out assuming that they're independent. So these two variables are independent of each other to prove that they are not. That's why that's okay. I wouldn't check it off. In general, for a chi-squared, the chi-squared assumptions is just that you have a random sample and 5 plus expected counts in each cell. We do also assume that the categories in each variable, that these locations are disjoint, and that the coffee types are disjoint, but I don't really bother with that one. So, because obviously, otherwise it'd be weird. Is there a significant relationship between coffee shop location and the type of coffee sold? State the hypotheses. The null hypothesis, let's snag it from the formula sheet, just says that the variables are independent. But that's not what I want. I want it to be question specific. All right. If you think about, okay, I'm writing this report for my boss. They don't want to see variables are independent. They want to see something like, now the null hypothesis, we always have to assume that there's no relationship until I have proof otherwise, right? I assume that the mean is some number until I have proof that it's less than that, right? And so there is no significant relationship between location, I'll just be sloppy here, and the type of coffee sold. You have to assume that they're independent, right? Until you have proof otherwise. And then HA is the same, but that there is a significant relationship. How can I? Well, you can just make my writing smaller. Convenient. There is a significant relationship between the location. What throws people off at this point, because you guys are really good about one-sided and two-sided tests, is that the chi-squared test is always just one-sided, but we treat it like a two-sided test. So it kind of loses that symmetry. But it's okay. The p-value is just the p-value now. Okay? And so I'm not upset if I see things like one-sided, two-sided at this point, because it just shows that you know about those things. This means that the chi-squared calculated You don't have to put the calculated on there, but I do find that it's helpful, is gonna be 20.5129. Depending on the degrees of freedom, that could be small, that could be big, right? And we're gonna find the degrees of freedom and the p-value or the critical value if you prefer. And maybe again, I'll try to make this smaller. Regardless, you're gonna need the degrees of freedom. Now from your formula sheet, it's the number of rows minus 1 times the number of columns minus 1 for, and I'll do shorthand here. I think I wrote it out, number of rows minus 1 times the number of columns minus 1 on your formula sheet, but I'm being lazy. I had 3 rows and 3 columns. You don't include the total. But no, I don't think anyone did. 1, 2, 3, 1, 2, 3. 3 minus 1 times 3 minus 1 means we have 2 times 2, so 4 degrees of freedom. I will snag the table from your formula sheet because I just give you a little snippet. It's all we need, really. We use software for anything bigger. Just itty bitty here, but I'll zoom in. If we have 4 degrees of freedom, I'm stuck here. Right. So then this here is your p-value. Or those are the p-values. So in the chi-squared scenario, I find that the p-value approach is harder than the critical value. So let's do the p-value approach first. If I have 4 degrees of freedom, what I'm gonna do is I'm gonna try to place my calculated chi-squared, just like we try to place our calculated t somewhere on the line. Here, I find that my chi-squared calculated, which is 20.5129, I'm going to set it up just as I would in the t situation or even the z situation, is I would have these less than signs. And what I find is that it's greater than 14.86. But it behaves the same, right? And so on the upper end, technically I would have infinity, although you don't have to put the infinity if you don't want to. So then the p-value is between 2 values. Fun. Let me just add on here at infinity, the p-value is 0, right? You can add and at 0, the p-value is 1. Could add should zoom in on that, little end caps on these if you want to. So then we know it's between 14.86 and infinity, helpful. So it's somewhere between 0 and 0.005. Or the critical value. I don't tell you what to use for your alpha. So you can use 0.05. So then I'll say let alpha be 0.05. Oops. I'll stay zoomed in a little bit, then the chi-squared critical, which is different from your calculated value, is 9.49. Which is just a threshold, right? On your chi-squared distribution, a general chi-squared distribution looks like this. Oops. So what we're really saying is if I force this area to be 0.05, then that happens at 9.49. And chi-squared is increasing as I move past there. And so just like t's, you could use the critical value approach for t's and z's. But if your calculated value is beyond 9.49, then you have enough evidence to reject H naught because, right, the area in the tail is smaller than 0.05. Right. They do the same thing. It's just a matter of choosing what you prefer. The assumed, if I don't give it to you, it's 0.05. Yeah. Yep. If you, well, what you could do is you could just say, I'm going to assume that alpha is this, right? But the default alpha is 0.05, just in kind of the world. So I'm expecting 0.05, but if you tell me that, hey, I'm going to assume that it's this, sure. You could even do something, it's a little bit strange. It's kind of like fishing in a way. You could say, okay, I'm going to let the alpha level be 0.005. You would still reject it at an alpha level of 0.005, but you want to just pick something from before you do your analyses and just kind of stick with that. So it's kind of less common to go that way, but nice. So then depending on which approach you use, if you wanted to do the p-value approach, then if the p-value is less than your assumed alpha level of 0.05, you have enough evidence to reject H naught. The tricky one is the critical value behaves kind of in the opposite way. It does the same thing, but the wording is opposite. And so our calculated chi-squared was 20.5129. It's greater, so it's beyond our critical value of 9.49. That means we have enough evidence to reject H naught in favor of HA. So there is a relationship between location and the type of coffee sold. And then the last little bit here is, and I did just follow through, whatever your conclusion was, if we reject H naught, you would be making a type 1 error if you made a mistake, right? Rejecting H naught when you shouldn't have. Rejecting H naught when we shouldn't. If you failed to reject H naught, which is you just kept H naught, right? Then it's a type 2 error. Failing to reject H naught when it should be rejected. We're mostly concerned about rejecting H naught when we shouldn't, right? Saying that there is a relationship between the location and the type of coffee sold when there actually isn't, right? That's worse than saying, nope, nothing's going on here, or generally worse. Nice. Better? Good.
For question 5 on the next page, for part C, is that very good? Cause I had that written first and then I erased it. And I changed it.
Let's see here. This one,
For C.
ABC.
One sec.
Oh, this one threw people off.
Yeah.
So, what is it? She's noticed that customers tend to spend more time lounging in the coffee shop during the winter months. She randomly observes 31 customers and finds that the mean lounging time is 30 minutes per visit with a standard deviation of 6 minutes in the winter months. So now we have one sample of the winter months with a mean and a standard deviation. Marge knows. She knows the mean lounging time in the population of summer months is 27 minutes per visit. This makes it the mu naught is 27. Tricky because it is a mean. I want to compare my sample mean to some hypothesized mean, but we haven't really seen it in that type of scenario. And so I did have quite a few people saying, okay, I don't have a standard deviation, and that's weird for this other sample, right? You're kind of look, what's going on over here? Lights are turning out. Kind of searching for that other sample size and that other standard deviation. And because you don't have those, then I would consider just a one sample mean, because then it'll become more obvious, right? That you want to find, okay, how far is 30? I want to compare it to 27. Right. So it's a one sample mean. That one was tricky though. It's probably the one that stumped a lot of people on this fire drill, mad minute style. What type of question is it? Now, what you can do is you can do all these for practice, and I'll post the solutions. I'm just realizing now I forgot to post the full solutions, but I have them typed up. So they'll be kind of shorter because typing them up is really annoying. And so, but just kind of brief, the T is this, blah, blah, blah. And then at least you can focus on your null and alternative hypotheses and the conclusion, which is usually where the most of the marks are anyways. Nice. Maybe I'll do this. Copy. Put it in the same notes. Any others?
I have trouble with question.
Okay. Which version? Oh. Slight oversight on my part. Surprisingly, the version 2 group did better, so I'm not concerned about it. But what's rude about what I did? This T is off the table, right? Okay. Let's just talk about
That's what I had, but I was confused because it was off the table, so I think that's what.
in version 2, right?
Yeah.
You found T was -5 point something. Nice. We'll pick up there. Is that okay? Yeah, because that's the most important part. How many degrees of freedom did you have?
18.
18. Nice. Okay, so we have the 18 line. You can do it. It's just that it requires a little bit more patience. Copy, which is a tough sell when you're writing a test. It's because I was making the new versions. And yes, I got sloppy and I was running out of time. So I didn't check the numbers. Or I didn't check them as thoroughly. Paste. But I also think I made you do it in both versions on test 1. So it's, I can explain it away, but it was my bad. So here, what you're gonna do at 18 degrees of freedom, let's just draw the t distribution out for a second here. T is still centered on 0, right? And we only use the positive values for t, right? But if we let the degrees of freedom be 18, then we're told that here at 0.688, so at t equal to 0.688, and I am building up to it. The area in one of the tails is 0.25. Then, if I mirror this, I can use a different color. Negative t is negative 0.688. The area in that tail is also 0.25. Right, going down to the one-sided. But there's a missing link here. Right? It's centered at 0. At t equals 0, the area in one of the tails is 0.5, and in the other tail it's 0.5 as well. So then the one-sided p is 0.5 and the two-sided p would be 1. What we want to do and what we need to do is we need to do that, but on the other side, right? And so here, kind of a leap, but we're off the cliff now, and next stop, infinity, right? Now at infinity, let's put it here. Then the area in the tail is 0. And kind of confusingly, even if you go to negative infinity, the area past negative infinity and and positive infinity is still 0, right? 0 times 2 is still 0. And so now you can still do it. Oops. I want those to go there. You can still do it at degrees of freedom equal to 18, we find that the absolute value of t equal to negative 5.3157 is between, so the absolute value is between 3.922 and infinity. So then, I can't remember if it was a one-sided or a two-sided test. So then the one-sided p-value is going to be between, now the smallest of these two is 0. So you're going to write that first. And the upper end, I think it's 3 zeros, 0.0005. Very, very small. Here, right? And then this. So they kind of crisscross applesauce there. because of the relationship. Nice, better.
Yeah.
And then once you have the p-value, you can do your conclusion, blah, blah, blah. Nice. You did it. All right. I'm gonna call it because you guys have another class. All right. Stop this recording. Have a great weekend. Bye, guys.